Oftentimes, reactions don't just happen in a single step and then it's done. They are broken apart and occur in sometimes a sequence of steps. And these smaller steps are called elementary steps. And if we look at every one of the elementary steps and how they add up to the total or the sum or the entire reaction, that is the reaction mechanism. So it's just that series of individual steps. It's called the reaction mechanism. So in this video, we're going to take a look at reaction mechanisms and the consequences of steps having different speeds. So a reaction mechanism describes in detail which bonds are broken and which bonds are formed. Let's take a look at this reaction. We have hydrogen plus this iodine chloride gives us hydrogen chloride plus iodine. Now what we see here with the balanced chemical equation is just one reaction, but this in reality occurs in a series of reactions. The first step is the hydrogen bonding with one or reacting with one of the iodine chlorides to create hydrogen iodide and hydrogen chloride. That's step one. Step two is this hydrogen iodide that's formed reacts with another molecule of the iodine chloride to create hydrogen chloride and iodine gas. So if we take these two reactions and we add them together, what that will do is it will allow us to cancel out items that are on both sides, both reactants and products. And one of the items that's on both sides is this hydrogen iodide. What you'll see is that it's formed in step one, but it's used immediately in step two. So what this is called a reaction intermediate. So it's a substance that's formed in one step and consumed in a later step of the reaction. Because it's formed and consumed within the reaction, you will not see it in the overall balanced equation for the reaction. So it ends up getting canceled out when we write the overall balanced equation. So let's take a look at how we add up step 1 and 2. We get hydrogen and the two iodine chloride compounds and two hydrochloric acid compounds and then the iodine gas. One thing I want to point out here is molecularity, and that is that elementary steps are classified by their molecularity, which is the number of reactant molecules that have to collide in order to form a reaction. And this will make sense when we get to reaction or rate laws. So in a unimolecular reaction, one thing turns into products. So the rate law for a unimolecular reaction is rate is equal to the rate constant times the concentration. And a bimolecular reaction requires a little bit more. It requires two particles to collide. So either two of the same particles or two different particles to collide. So the rate law for a bimolecular reaction looks like this. Rate is equal to the rate constant times the concentration of A squared. Or if we have two different substances reacting, so A plus B give us products, then the rate law for that will be rate is equal to the rate constant times the concentration of A times the concentration of B. We can know these rate laws. And by the way, a termomolecular reaction is where three things need to collide. That rarely ever happens as a elementary step, so we're not going to worry about it too much. We can determine the rate laws for elementary steps using their equations and knowing if they're unimolecular or bimolecular. We cannot determine the overall rate law for an overall reaction without doing an experiment. So in most chemical reactions, there's usually one step that progresses slower than all the other ones, and this is called the rate determining step. So let's take a look at this reaction. This reaction has a slow initial step. So we take NO2, combine it with carbon monoxide to give us NO and carbon dioxide. The elementary steps are as follows. So step 1, the nitrogen dioxide reacts with another nitrogen dioxide molecule to give us nitrogen trioxide and nitrogen monoxide. This is the slow step. The second step is the fast step. So the nitrogen trioxide reacts with carbon monoxide to create nitrogen dioxide and carbon dioxide. This slow step has a rate law of rate equals K times the concentration of NO2 squared. This is our slow step. This is the step that dictates how fast the reaction will go. After that, the second step is really fast and it'll just go right away. So the entire rate law for the reaction is just based on the rate law of the slow step. That's kind of like your bottleneck in a chemical reaction. So if you can determine what your slow step is, you can actually determine the rate law a lot of times by looking at the reaction mechanism. So here's what's called a reaction pathway, and you've seen these before. This is just a graph of energy versus reaction progress. But what this picture does is it shows the different steps in a reaction. So after we've reached that first activation energy, we get activated complex number 1. Then we have a low point, a low intermediate. This is that in our example, this would be the HI that was consumed right after it was produced. Then we have another activated complex. We'll call this activated complex 2 upon reaching the second activation energy. And then we have products. So step 1 has an activation energy. Then we have our intermediate. Then step 2 has another activation energy. And then we have our products. That first step has its own activation energy, so EA1, and the second step has its own activation energy, so EA2 there. And each step, by the way, has its own activated complex as well. Remember that super unstable kind of molecule with the weakened or twisted bonds? This reaction, by the way, is exothermic because the products have less energy than the reactants.